Hi, everyone. Today we are going to unravel the mystery that is polar bear fur. So I actually want to start off by giving you some fun facts that kind of seem magical until we dive into the scientific principles behind them. So the first is that polar bears have black skin and clear hair. But we all know that they're white. The second is that they can survive in temperatures as cold as -50 degrees. And we all know that that is very cold based on the temperatures we had just the other week. And lastly, you cannot take an infrared picture of a polar bear. And the answer to why all of these are true is because of electromagnetic radiation. So let's look at number one first, and I'm going to sketch out what the polar bear fur and its underlying structures look like. So we have this thick layer of blubber, like a lot of Arctic animals do, to help retain warmth. And then above that, like I mentioned, this dark pigmented skin. On top of that, there is this short but thick and dense layer of fur called underfur. And protruding out of that, we have these longer hairs that are called guard hairs. And these are made out of keratin, and pure keratin is actually translucent. So that's why they're clear. And these hairs are also hollow. So guard hairs, they're made of keratin, they are clear, and they are hollow. So let's actually zoom into what one of those would look like. So if I draw that down here, kind of sideways, here's our long hair, and we have that hollow medulla on the inside. But it's not just completely hollow. There are actually these structural bridges of keratin that extend from the keratin up here to down here, and they're evenly statistically spaced apart to kind of create this micro labyrinth within the inside of the hair. So let's label these keratin bridge or bridges, and then these are air pockets or voids. So this kind of resembles the structure of a fiber optic cable with a few differences. But let's look at what actually happens if light were to hit the structure. So if I just kind of zoom in and draw a couple different ones next to each other. What happens when light comes in? So we get solar radiation, light coming from the sun, and the light gets coupled into the hair. So light coupled in. And now there are a few different options that we have from here. So the light can either be scattered back out, but if we see what happens when that gets scattered out, it's just going to get coupled into the next hair here. So we get kind of this cyclical process of coupling into adjacent hairs. And then it can get scattered back out of this hair and go on to the next hair, and so on and so forth throughout the entire pelt. But there are other options for what this light can do as well. So the light could instead be internally reflected, or not even just instead, but part of the light could be doing each of these processes. So it can be internally reflected and kind of just stay within this one hair. And again, like that could, down here, it could end up being scattered out. And so these are kind of cyclical processes that, that happen. And the last thing that could happen and with that initial coupling in is keratin luminescence. So keratin is a protein that when it gets excited by a certain wavelength of light, it will emit light. And the light that it emits, I'll draw that as kind of like a little firework looking thing. The light that it emits can then go through these same processes as well. So you can see this gets really interconnected really fast. And you get like these different processes that are all happening at once to scatter the light around. The light isn't getting absorbed, it's just being bounced around and around. But this still doesn't answer the question of why are polar bears white? So what actually happens is all of this bouncing, but there is a small fraction of the light that bounces right back out into the environment. And so we'll say scatters out here, and this is what's known as backscattering. And like I said, none of the wavelengths of light are getting absorbed by these structures. It's just getting bounced around. So all of the wavelengths of light are being reflected back in this backscattering process. And when all of the wavelengths of light are being reflected back, that is what gives us the white color of the polar bear. And you're probably thinking, wow, that's cool, but what happens to all of that light after it's just bouncing around? Does it just bounce around in there forever? Well, once the light gets down far enough into the underfur that I mentioned before, it actually gets converted into heat. Or if it bounces around enough before that, it actually just dissipates as heat. And in the underfur, it can trap the heat, and that helps to keep the polar bear warm. But let's look at what the scattering actually looks like mathematically before we dive into the heat. So the scattering itself is a process called Mie scattering. And I really don't know if I'm saying that correctly, but that's how you spell it anyways. And mathematically, that can be represented by the Fresnel coefficient, which looks like this weird symbol. And you have the refractive index of your first material minus the refractive index of the second over the refractive indices summed, and then the whole thing squared. So you can see from this equation that you have to have two different materials with two different refractive indices in order to get the scattering to happen. That's really key. And then also, because it's squared, it doesn't matter which material the light is traveling through first, you're going to get this positive coefficient that's going to lead to the scattering. And so that's kind of important when we think about the different options of what's happening here. So when you have light that's coming in from the external environment, so this sunlight coming in here, the arrow that I've just bolded, the air is going to be that first material. And then the second material is going to be the keratin in that case. And that's what's going to cause that scattering. You'll get that positive coefficient. But when the light is already coupled into this fiber, so it's within the inside, the hollow medulla, then the first thing that it's seeing for a material is actually keratin, right? And so we know that because it's already hit keratin here, that in order to scatter, it can't hit this keratin bridge because that would be the same refractive index. And so the voids actually act as the scattering centers once the light is coupled into the hair. And so that's why this bidirectionality of the Fresnel coefficient is really important, because it doesn't matter which is which, we just end up getting scattering either way. And it's also important for creating that white light. So air particles, the size of them, particles, are much smaller than the wavelengths of the light that are hitting them. And that is actually the phenomena that allows for independent wavelength scattering backwards. And as I mentioned before, when it doesn't matter what wavelength is being scattered, none of it's being absorbed, so everything is being scattered back, we get that white color of the polar bear. So that white color is really key for the polar bear as it allows them to camouflage with their Arctic environment. But as promised, I will also talk about the heat that this generates, which is also important for the polar bear because they really need to stay warm. So if we kind of come back up here, let's kind of summarize what we've just talked about. So we have the light coming in, and it goes scatter, scatter, scatter. You know, there's all those different processes, and some gets reflected back as white light. But as it gets down here, it's scattered until it reaches this thick, dense underfur. And here, I don't want to write on this, absorbed as heat. Sorry, I'm writing over things. Let's do that. Absorb as heat. So that allows the light to be transformed to heat. But you also have, on the flip side of things, the heat radiating out from the body. So we all have heat that radiates from our body out into the environment. But in the polar bear, that heat just gets radiated out into this dense underfur, and then it's cyclically trapped within there. So because you have these nice air spaces within the guard hairs, those can act as actually an insulator for the heat within the polar bear's body. And the micro labyrinth of the keratin bridges and that air, it really helps to keep all of that thermal radiation just bouncing around within the polar bear's fur. And that is what allows them to not only stay warm, but be thermally invisible because they're not actually projecting any of that heat into the environment. So they have no heat signature that can be picked up with infrared imaging. So that's really interesting. And mathematically, we can look at that as well and kind of tie this back together as to why they're scattering the light around and still maintaining their white color. So if we look at the heat flow, there's a bunch of derivations here, but you end up getting heat flux is equal to transparency times the absorbance of the skin. So I'll just note skin over 1 plus the thermal conductivity of the pelt over the thermal conductivity of the skin. And so from this, we can see that in order to optimize this parameter, we would want to increase the transparency, which the polar bear has done. It has completely clear hairs, as well as increase the absorbance of the skin, which also the polar bear has done by having that dark pigmented skin that's more easily able to absorb the light. We also want to actually increase the conductivity of the skin. So the skin actually, we want it to emit some of that heat into the underfur and keep it trapped there. And then we want to decrease the thermal conductivity of the pelt so that it remains trapped in there. And all of that allows the polar bear to retain that heat. But at the same time, as we just went through with the Mie scattering, it allows it to stay white. So it balances that camouflage with its need to stay warm. And then it's just an additional consequence that they end up being thermally invisible.